The topic of this lecture will be predicting whether SN1 or SN2 will predominate. It's useful to be able to determine whether SN1 or SN2 will predominate with a given set of substrate and nucleophile, because this allows us to better predict what the products will be in terms of the product stereochemistry and whether or not rearrangements will occur. Remember that when we're saying that the SN1 or the SN2 mechanism predominates, what we're really saying is whichever mechanism predominates is happening more quickly. The rate of that mechanism is more quick, and therefore the products that result from that mechanism are formed as the major products. So what we're really talking about when we compare the SN1 and SN2 mechanisms are which one of these mechanisms has the fastest rate. First, we'll look at the effect that the nucleophile has on the rate of an SN1 and an SN2 reaction. Remember that it's only the rate of an SN2 reaction that is affected by the structure of the nucleophile. The rate-determining step of an SN2 reaction is bimolecular, meaning that both the substrate and the nucleophile are involved in the rate of the reaction. In an SN1 reaction, the rate-determining step is unimolecular. Only the substrate is involved. Therefore, changing the structure of the nucleophile does not affect the rate of an SN1 reaction. A stronger nucleophile will speed up an SN2 reaction, so a strong nucleophile is said to promote an SN2 mechanism. A weak nucleophile slows the rate of the SN2 reaction. This means that the reaction is more likely to go by the SN1 mechanism, especially if the substrate favors the SN1 mechanism. Next, let's look at how the substrate affects the rate of an SN1 versus an SN2 reaction. Because the substrate is involved in the rate-determining step of both the SN1 and the SN2 mechanism, the structure of the substrate affects both the rate of the SN1 and the SN2 reaction. Methyl and primary substrates are poor SN1 substrates. They slow the rate of the SN1 mechanism because the carbocation that is produced is very unstable, therefore it forms very slowly. However, methyl and primary substrates are good SN2 substrates because the lack of steric hindrance around the leaving group allows a close approach of the nucleophile to the electrophilic carbon. On the other side of the spectrum, tertiary substrates are too hindered for SN2 reactions. The steric hindrance around the electrophilic carbon attached to the leaving group slows the approach of the nucleophile, slowing the rate of the SN2 reaction. Tertiary substrates make good SN1 substrates, however. This is because the tertiary carbocation that is formed is very stable and therefore forms very quickly, speeding up the rate of the SN1 reaction with tertiary substrates. Secondary substrates are in between. These substrates can go SN1 or SN2 depending on the other factors in the reaction, the solvent and the nucleophile. Next, let's look at the effect the solvent has on the rates of the SN1 and SN2 mechanisms. Because the SN1 mechanism involves charged intermediates, it benefits the most from a polar protic solvent. A polar protic solvent is able to stabilize the transition state that looks like those charged intermediates, which lowers the activation energy, speeding up the mechanism. An SN2 mechanism, on the other hand, benefits most from a polar aprotic solvent. A polar aprotic solvent is very good at dissolving the reactants. Additionally, it does not weaken the nucleophile like a polar protic solvent does. Because an SN2 reaction requires a strong nucleophile, this helps speed up the SN2 reaction, allowing it to predominate in this type of solvent. Considering the structures of the nucleophile, the substrate, and the solvent can help us predict whether the SN1 or the SN2 mechanism will predominate, allowing us to make predictions about the structures, the stereochemistries, and the rearrangements of the products.